Irreducible complexity can be illustrated by a familiar, non-biological machine, a mousetrap. The trap is composed of 5 basic pieces: a catch to hold the bait, a strong spring, a thin bent rod called the hammer, a holding bar to secure the hammer in place, and a platform upon which the entire system is mounted. If any one of these parts is missing or defective, the mechanism will not work. All components of this irreducibly complex system must be present simultaneously for the machine to perform its function. Catching mice. The concept of irreducible complexity also applies to biological machines, including the bacterial flagellum.
All told, there are about 40 different protein parts which are necessary for this machine to work. And if any of those parts are missing, then either you get a flagellum that doesn't work because it's missing the hook or it's missing the drive shaft or whatever, or it doesn't even get built within the cell. You can't put something like that together gradually because they need a large number of parts interacting with each other at the same time before they work at all.
Without the tools to observe the machinery of the cell, and long before the idea of irreducible complexity, Charles Darwin offered a way to test his own theory. In Origin of Species, he wrote, "If it could be demonstrated that any complex organ existed, which could not possibly have been formed by numerous, successive, slight modifications, my theory would absolutely break down."
Darwin acknowledged that if someone identified a biological system that could not have been constructed in incremental steps over long periods of time, then his theory would be invalid. And what Michael Behe and others have discovered is the existence of biological machinery that cannot be explained away by Darwinian processes. Darwin's failed predictions have in fact falsified his own theory. The existence of complex biological machines raises an obvious question. If natural selection wasn't the agent of their construction, then what was? The centerpiece of my investigation was an interview with philosopher of science, Dr. Stephen Meyer. Meyer, who holds a PhD from Cambridge University, brought me face to face with the most efficient information processing system in the universe. The DNA molecule and its language of life.
The discovery of the information-bearing properties of DNA and RNA is a fundamental challenge to all materialistic theories of the origin of life. Neo-Darwinism and its associated theories of chemical evolution and the like will not be able to survive the biology of the information age, the biology of the 21st century.
Meyer's conclusions are based upon his understanding of the DNA molecule and the genetic instructions that are locked within the nucleus of living cells.
In 1953, when Watson and Crick elucidated the structure of the DNA molecule, they discovered that DNA was a carrier of genetic information in the form of a 4-character digital code. That is to say that DNA functions like a software program, only more complex than anyone has ever created or devised. For a biological system to run and operate, it needs genetic information to build the proteins and protein machines that cause the cells to maintain their function.
This information is stored in a precise arrangement of 4 chemicals that scientists represent with the letters A, C, T, and G. Sequences of these chemicals provide the instructions necessary to assemble complex protein molecules that in turn help form structures as diverse as eyes, legs, wings, and hearts. This code has been called the language of life, and it is the most densely packed and elaborately detailed assembly of information in the known universe.
Geneticist Michael Denton has estimated that the amount of biological information necessary to build all of the proteins in all of the species of organisms that have ever existed on planet Earth could be held in a single teaspoon. and we'd still have room left over for all of the information contained in every book ever written. The more I learned about DNA, the more I understood the significance of what Stephen Meyer called the most fundamental question facing biology